Well, thank you everybody for joining us today for the professional series, first in the professional series of the Climate Ready Landscape Academy, Outdoor Water Budgeting. I know this is a topic that's important to a lot of us in the landscape industry. We are going to spend the next few hours going through these 6 topics. We'll start with reviewing the watershed approach and talking a little bit about how we measure water. We'll review the plant water requirement, and then we'll just jump right into landscape water requirement and the water budget, which is called the MAWA, or Maximum Available Water Allowed. There are a lot of acronyms in this presentation. We try to make it easy by referring to things as the budget or the plan. There's just no getting around some of these acronyms, so stick with it. The 4th thing that we will talk about is the plan, the design plan. How much water have we designed into our new landscape that we are trying to evaluate for water requirement? And that is called the estimated total water used. Yeah, that one rolls off your tongue. Stick with the plan. Then we're going to talk about how we account for precipitation in all of this, because of course that's an important part. And as landscapes are becoming more important to outdoor water conservation, we need to think about how precipitation fits into offsetting irrigation, but also how precipitation changes really the whole way a landscape functions. So we will spend some time on that. And then finally, love to wrap it up with soil. The soil sponge changes everything. So everything that we learned up to then, we're going to throw on its head and talk about how soil management actually alters a lot of our preconceived notions about water budgeting. So the first part here is the watershed approach and measuring water. Everything that G3 talks about comes back to this concept of the watershed approach to landscaping. And essentially, this is a framework that allows us to look at every single landscape as though it is a mini watershed. And what that means is we are looking at landscapes and trying to improve them so that they begin to function like a balanced watershed would function without intervention of humans. This is a very holistic, I hesitate to call it a sustainable approach, because the truth of the matter is our landscapes, especially in urban and wildland interface areas, is so degraded that we don't want to sustain it. We want to regenerate it. But in some places, it's called sustainable landscaping, holistic ecosystem, ecological landscaping. These are all terms that kind of refer to this idea of trying to get back to functionality that is more balanced and mimics the balanced watershed. And just to review very, very quickly, essentially what this is doing for us is we're allowing ourselves to think about the landscape as a place where water cycles through the landscape. So all the water that comes from the sky, we are able to capture and infiltrate down into the soil, either to allow it to percolate down to refill the water supply in the water table, or to journey to the local river, stream, etc., lake, in order to recharge the water in those water bodies. And we're also then thinking about not only the water coming into the landscape, but also how water goes out of the landscape. And this is primarily through something called evapotranspiration, which we'll talk about in just a second, where water is actually being transferred from the soil up into the atmosphere again as water vapor. And there are things that landscapes do, plants and soil, are actually really critical in the cycling of that water to come back onto the land. And so we really want to try to create these landscapes that are thinking about not just how much water is demanded by the landscape, but how is that water supplied naturally? And beyond water, the cycles of carbon, the cycles of nutrient, these are all really important aspects of what's going on in a landscape. And that's what the watershed approach is about. And essentially, for this particular workshop, we are going to do something kind of odd in that we're going to focus on really primarily on two aspects of the watershed approach. But the watershed approach has four components. There are four principles. We are we're building healthy living soil and we're capturing rainwater, but then we're selecting local climate appropriate plants and we're utilizing highly efficient supplemental irrigation only when necessary. And when we talk about water budgeting in landscapes, at least conventionally, uh, we really begin to home in on the local climate appropriate plant selection and the highly efficient irrigation. And that is what drives the calculations for how much water demand a particular landscape has, those two elements. Now, as we're going to find out in this presentation at the end, holding on to rainwater and building healthy living soil actually change a lot of our assumptions about water budgeting. But for the purposes of going through the calculations, thinking about it from a regulatory perspective, many states in the country are adopting water budgeting approaches to water management. And so to really, keep the story to that, to apply to that, we are going to be focusing on the plants and the irrigation. Now, irrigation measures water in inches, or if we're talking about volume, we're talking about cubic feet of water. Very convenient, right? And in order to determine water volume, we utilize a water meter. Now, I'm not going to spend a lot of time going through how to read a water meter, but for many people, the water meter is kind of a scary thing. It's in a box somewhere on their properties. If it's a residential client, uh, it's in a box. It's got a lot of, it could have insects in it or critters. And so, you don't go there unless you absolutely have to. And yet, this is an incredibly important device for us in order to manage water in our landscapes. And if we want to become better professionals with regard to water budgeting and to managing landscape irrigation, we really need to get comfortable looking at the water meter and utilizing it, for that purpose. And so, to quickly kind of review, as you probably know, there are essentially analog and digital meters. The analog meter is really like reading an odometer. It can either appear in cubic feet or it can appear in gallons. When you have one of these dials, it's essentially, like, as I said, like reading an odometer. The couple of things just to keep in mind are that there will be a sweep hand, which is moving around and showing usually either gallon or 10-gallon units. And these are not, when we read the meter, we don't really take those into consideration until they reach 100 gallons. And I'll talk about that in a second. But this is this is the thing that everyone notices is it's going around, the sweep hand is, but it isn't actually moving the dial until there's an entire revolution. There is a leak indicator usually on these meters, which is that little flag or some, in this case, this little triangle, which is going to be moving if there is a very low flow. And we use that especially in our leak detection process. There's also usually information about the pipe diameters of the inflow pipe and the outflow pipe on the meter. And in general, we read these from left to right. So in this particular case, the 2 is indicating 100 cubic feet. And so this is 200 cubic feet on this reading. And we would not really be taking into consideration the cubic feet beyond the 2, the number 2. So we'd really only be reading the first 4 numbers here. In order to convert cubic feet into gallons, we need to multiply by 7.48 gallons per cubic foot. And it's an inconvenient calculation. And we're really going to be focused in this particular workshop more so on the 748 gallons per 100 cubic feet. So as I mentioned, these meters are generally read in 100 cubic foot increments or larger. And so when we see, for example, the last meter reading was 200 cubic feet of water, we would multiply that 200 by 748 gallons, and this would tell us, I'm sorry, we would multiply the 2 by 748 gallons, and that would tell us how many gallons of water we have. So in our example coming up, we're going to have a reading that says 35 units were used during a period. Well, what the heck is that? Well, a unit is also 800 cubic feet. And sometimes this is indicated as CCF, which is the Roman numeral C for 100 cubic feet. They all mean the same thing, 748 gallons. So a 35 unit reading or a 35 unit measure would be equal to 26,180 gallons of water. Now, it's important for us to just take a second because I'm spending time here on converting from the volume of cubic feet into gallons, and it seems like it's not really relevant. Well, the thing about talking about water with people, whether they're in water supply agencies or stormwater agencies, or they're customers, residential customers or commercial customers, everybody has a different perception of what volume of water should look like. And so it's really important for us to be able to think in units that allow us to convey something of value to the end user. So when we're talking to residential customers in particular, and perhaps even commercial customers where we're trying to convey information about their landscape, we're going to have to convert into gallons. And I'm going to show you in a little bit how we do that in the landscape context. But here, units times 748 gallons per unit gives us gallons. If your meter is reading in gallons already, lucky you. Generally, these are read in either 100-gallon increments or sometimes 1,000-gallon increments. In this particular case, you would not be reading the 2 numbers in black. You would be reading the 3 and maybe 4 numbers on the left. And in this case, it's 126, and this is 126, that 100 gallons. So 12,600 gallons of water. It's hard to do without a pen and paper, quite honestly. So it's 126 hundreds gallons, which is equal to 12,600 gallons of water. We don't read the 70 at the end. If you have a digital meter, it's a little bit different. Something that's cool about digital meters is that you have the meter reading again from left to right, and usually in 100-gallon increments. So it's read exactly the same as it would have been with the analog meter. But on a digital meter, you also have this bit of information which is super helpful, and that is it will switch between reading off the amount of water that has gone through the meter with the rate of the flow of the water going through the meter. So this is kind of your it's a little bit of a leak indicator, but it's just to indicate that in fact there is water going through this meter. The screen will flash and another number will come up, like this very small number that you see here, 0.04. And this is telling you how many gallons per minute are going through that meter. So if there's no water flowing, that's going to read at 0. But if water is flowing, this is going to tell you how many gallons per minute rate that water's flowing through. Actually kind of helpful when you're doing irrigation controller programming, but we'll talk about that in another class. And then finally, on most of these meters, there is some kind of low flow indicator. And in this case, it's a little faucet. You can kind of see it in the left-hand corner of the lower black box. And this will flash. And it basically is saying, hey, something's going on, something's leaking. If it's on, persistently, there's definitely a continuous leak and you need to look into it. So digital meters are replacing analog meters in a lot of areas. But they're all really important because in order to manage our water use on a landscape and know whether or not the water that we have planned to use is actually being reflected in the actual water usage, we need to have a meter in order to do that. Your water bill is going to reflect the reading from the meter. That kind of makes sense. And the bill is usually stated in 100 cubic feet. Sometimes it's just stated outright in gallons these days, but if you have a cubic foot meter, it will actually be read as 100 cubic feet. So you're going to have to do that little multiplication of 748 gallons per one unit, 100 cubic foot unit. And you see here again that calculation of 35 units times 748 gives you 26,180 gallons. Now the question I have here, so that is the reading from this particular billing period. The previous period was 2,097 100 cubic feet, and the current reading is 2,132 100 cubic feet. So tell me, so that's how you came up with the 35 units. That's the difference between these two readings. But the question I have for you is, how much water have these people been saving since in the same period since 2017? In other words, in 2017, they used 65 units. This period, they're using 35 units. How much have they saved? And just take a second. It's pretty straightforward. It's going to be 65 less 35. Kind of get us started, just getting our brain started here. And basically, the difference is 30 units. So we would multiply 30 units by 748, and that would give us 22,440 gallons. So this customer has actually reduced their usage in the same time period by 22,440 gallons. Good on them, right? That's excellent. Water suppliers are usually talking about water in far larger volumes than cubic feet or 100 cubic feet even. They are talking about water in acre feet. An acre feet is, you see here, 325,851 gallons. Let's call it 326,000 gallons. And then when you're really talking about volume, and maybe annual water supply, or you read in the press about deals that are being made in the water industry, and they talk about million acre feet. And so this is taking that 326,000 and multiplying it by 1 million. It's a lot of water. An acre foot is basically enough water to cover the area of about a football field with 1 foot of water. So that's kind of a good visual on it. And it's usually enough for a family of four, for two families of four. So, it's not 8 people living in the same home. It's actually 2 families of 4 people, both their indoor and outdoor water use. That's about an acre foot a year. And that is coming down because people are conserving, and devices, especially indoors, have helped people conserve. Another measure that we're going to want to know or understand is what I referred to earlier as evapotranspiration. Evapotranspiration is a measure of plant water use. Now, you will hear this referred to as plant water demand. Plant water requirement is what we are going to calculate from this. But this is a measure of how much water a particular plant is removing from the soil water supply and turning into water vapor and putting out into the atmosphere. It's composed of 2 pieces. When we measure it, we actually measure evapotranspiration with a weather station. And so we are measuring both the evaporation of water from the soil surface. And in this case, I'm calling that lost from the soil surface because evaporation is a lost cause. Water is not doing any benefit when it's evaporating. But then we have something else here called transpiration, and transpiration is intermediated by the plant itself. It is essentially the plant pulling that water out of the soil profile, converting it into water vapor, and putting it out into the atmosphere. Now, evapotranspiration is expressed in inches of water over a period of time. So we talk about a plant or a system evapotranspiring X inches per day, per week, per month, per year, etc. So there's always a time period associated with evapotranspiration. And the major determinant of transpiration, which is the biggest part of evapotranspiration, is basically solar radiation. And so in this case, what we're basically saying is that the transpiration is like a plant sweat. It's a response to the very hot business of having to photosynthesize. So you've got those leaves out there, they are gathering sunlight to convert carbon dioxide out of the atmosphere into sugars and all other kinds of things, and split the atoms and put the oxygen back out. I mean, this is basically it's akin to a nuclear reaction, frankly. And so so the plant is doing this through its leaves. It needs to cool itself off. Like any good power plant, it needs to cool itself off. And when the sun is high in the sky, when the days are long, the plant is going to be sweating more. And we can actually look at different plant structures, different plant responses to solar radiation, and determine whether or not that plant is adapted to its particular site, and so therefore is able to reduce its transpiration. It has a low transpiration rate, or there are plants that just aren't adapted to their particular conditions, and they are going to be responding to this solar radiation very unhappily. They're sweaty plants, and they are going to be transpiring very rapidly. So obviously, whether a plant is a high transpiration plant or a low transpiration plant is going to have an effect on the water budget. It's going to have an effect on irrigation, because this is essentially a measure in inches of the amount of water that is being removed from the soil water profile. And so this is really at the heart. Evapotranspiration, and in particular transpiration, is really at the heart of all of everything we discuss in irrigation and plant water use demand. Okay, Enough about measuring water. Let us do a quick review of plant water requirement. So plant water requirement takes evapotranspiration data and begins to apply it to a particular plant to quantify it and allow us to make decisions about plants, decisions about our landscape. Essentially, it's a calculated number, the plant water requirement. And I want to emphasize that it is a measure again of the inches of water that is being removed from the soil by an individual plant. It's really important for us to remember that plant water requirement is an individual plant. We, in water budgeting, are going to apply it to groups of plants in the landscape. But in reality, it is just a measure of an individual plant's removing rate of removal, right? Inches over a period of time, a rate. There are two components of plant water requirement. And the first is getting kind of a baseline on evapotranspiration that allows us to take a look at other plants in a in a particular area and make guesstimates about how much water they would require. And so there's an ingenious system that really came from agriculture, where the evapotranspiration rate of alfalfa was originally viewed as something that farmers would be very interested in understanding. Alfalfa is a pretty high water demand plant, and if you grew alfalfa in lots of different areas and you measured the evapotranspiration rate of that alfalfa, you could kind of begin to make assumptions about the conditions in which that alfalfa was growing, because it would be evapotranspiring at different rates in different places. Well, that agricultural notion got transferred to landscaping through the reference evapotranspiration rate, or ETO, which is a measure of the evapotranspiration of a perfectly grown turf grass. And this is a cool season turf grass. It is grown in these perfect field plots all across the nation. And weather stations will monitor the conditions, the weather conditions in the particular place, and also measure the evapotranspiration of that turf grass in that particular place. And so when we look at reference evapotranspiration, or what I'm going to start calling ETO, so it's evapotranspiration observed, ETO. This is the reference inches of water over a period of time that cool season grass is removing from the soil when it's grown as a monoculture in full sun, in perfectly maintained conditions of 4 to 7 inches tall, no lack of water. It's given plenty of water. It's an open space, so it doesn't have any buildings or anything, trees or anything shading it. So this is like perfect grass. And so when we grow perfect grass in a plot, stick a weather station on it, we're able to measure the evapotranspiration of that grass in that particular plot. And if we are growing grass under the exact same parameters in different places and measuring that evapotranspiration, we can essentially refer to this evapotranspiration rate as the reference point, because it's a uniform crop grown, exactly same conditions, measured exactly the same. And the differences then that we see in that evapotranspiration rate reflect the environmental conditions, the weather conditions in that particular place. Reference evapotranspiration rate, ETO. It's the baseline evapotranspiration rate. In California, there is a wonderful system. California, being a very large agricultural state, has developed and also a very large landscape state, has evolved this California Irrigation Management Information System, or CIMIS. And this is essentially a network of 145 weather stations that are located throughout California, and they are sitting on these perfect plots of cool season grass, and they are measuring evapotranspiration in these particular places. Now, with the use of satellites and some other AI and so forth, uh, the CIMIS has been able to use these like live weather station observations and do some interpolation in between the places where there isn't a weather station, sitting, in the same city or town or block, where you are. But you are able to use a weather station that's near you, and then have the data interpolated to tell you what the reference ETO, that was redundant, what the reference evapotranspiration rate is in your city. And so when you go to the CIMIS website, you log in and you go to data, and data is going to give you a list of these stations. And you are going to find a station that is um, in a similar geographic and weather situation as you are. So to be clear here, when you're using these kinds of data sets, yes, of course, you start with, oh, is there a weather station in my town? Okay, at my zip code. Yes, okay, let's find that. But then you need to do a little bit more thinking about it if you want to get precise, or if you really want to get a handle on what you're managing, and think about, that weather station is sitting at a higher elevation than where I am. Is there another weather station that might not be in my zip code, but it is in a similar geographic condition as I have? Would that be a better representation of ETO? This is up to you as a manager of water, but I put it out there because it is something to think about. This is a wonderful system, and I'm not knocking it at all. You can just use the one that's in your zip code. But in this particular case, I'm showing you that. Wait a second. Yes. So you find the weather station, and then you click on the weather station, and it will read out data, daily, weekly, monthly, annual ETO data, reference evapotranspiration data for that weather station. There's also a ETO measuring system that NOAA has. This is the evapotranspiration water management aid. You can go here, and it actually has a interactive map that allows you to go in and click on a region or a particular area and get daily ET. So that's that's good if you're doing irrigation management. And then for our purposes in water budgeting, this is probably one of the better tools for doing generalized water budgeting. And this is the EPA's Water Budget Data Finder. Here, you are going to be using your zip code in order to go into the 3 data sets that they have to gather information about the conditions in your area. And so you can get this monthly ETO by going into that data set. You can get rainfall in inches by going into that data set, or really great is going into the peak watering month data set. And this is essentially showing you the maximum ETO, like figuring out when is the maximum ETO less rainfall inches, what month is that where that occurs? Because that's going to be your peak watering month. Obviously, if you're not getting rainfall and your ETO is high, that has to be made up by supplemental water. And so this is telling you the peak watering month. And when you go into the peak watering month tool, you put in your zip code, and it is going to tell you the ETO value and also the rainfall for that month. And you can then use this peak watering month data to project your water requirement for the rest of the year, or certainly if you're in a place that doesn't have a complete year of growing season, you have a limited growing season, this can help you to project the water demand for the growing season, May to September, let's say, or May to October. And I've put in here a couple of examples of zip codes just to give you some idea about, how different things are. If you look at this, you can see that in Los Angeles probably has the highest peak watering month in July at 6.5 inches because they have no rainfall. But actually, Bend, Oregon, Bend, Oregon is higher because the peak watering demand is 7 inches of ETO in that month, less rainfall of only 1/4 of an inch. So this is going to be 6 3/4 inches of like net ETO. So you can see that evapotranspiration doesn't have well, I was going to say doesn't have that much variation. It does actually have variation, but the net, it's very interesting when you look at the net. It's a pretty narrow range, actually, during the peak watering months, and that makes sense because evapotranspiration is driven by what? Yeah, solar radiation. And what's happening in the summertime? Long days, lots of solar radiation. So of course, they're going to be pretty similar. Okay, that is reference evapotranspiration. It is based on a uniform monoculture of cool season turf grass. We're measuring the amount of water in inches coming out of the soil and going into the atmosphere. But how does that help us if we're not planting turf grass? Right? We're going to be planting something else. So we need to be able to compare other plants to the reference evapotranspiration to figure out how much water this particular plant is going to require in this area without having to grow out a whole field of it and put a weather station on it. And the way we do that is by using plant factor. Plant factors are essentially percentages of ETO that are required by a monoculture of a particular plant. And it compares, it's an estimate of plant water requirement, and it compares the individual plant with the reference plant cool season grass. And it says essentially, does this new plant, in this case, we have a picture of lavender here, does this new plant require more water than the reference plant, than cool season grass? The answer is going to be no. I'm comparing my lavender with cool season grass, and I'm saying, does this plant require more or less water than the cool season grass? Generally speaking, the more water is very particular conditions. Riparian conditions may be, it can be calculated to have a plant factor greater than 100%. Okay, but in our particular case, we're just looking at factors that would essentially decrease the water requirement of a plant or make it equal to cool season grass. And so here what we're doing is we're saying, hey, how much less water than cool season grass does a lavender need if it's grown in perfect conditions in this particular place? So that's a good question. And, as I said, we're not going to grow out fields and fields of every plant that is in a landscape or could be in a landscape and stick a weather station on it, in every locality and try to measure, the evapotranspiration of that particular plant. No, instead, we've got that going on with cool season grass. And now we're going to come up with a percentage of the cool season grass evapotranspiration that we can apply to this particular plant. So for every climate zone, each plant is going to have its own plant factor, and it is expressed as a percentage of ETO in that particular climate. So lavender in Los Angeles is going to be a percentage of the Los Angeles ETO, and lavender grown in Des Moines, Iowa is going to be expressed as a percentage of the ETO in Des Moines, Iowa. And it's possible that when lavender is grown in Los Angeles, it has more adaptations. And so it requires even less water than it would need in the super hot, humid conditions of Iowa. So it could be a lower percentage in California or in Los Angeles than in Des Moines. So this is what we're going to do now, is try to figure out how do we assign these plant factors, because that sounds pretty complicated. It's not. So again, plant factors and the resulting plant water requirements are expressed as a percentage of the local ETO. So I figure out my local ETO. So in this particular chart, we have an ETO that's a little bit more than 50 inches, 55 inches almost. And if I were to say, what is the plant factor of that? And it's a little, yeah. If I were to say, what is the plant factor of that particular plant? I'm not saying it is cool season grass. I'm saying it's that particular plant that is growing at, 100% of the ETO of cool season grass. My plant factor is 100%. But if I have a plant in the same place that is a moderate water use plant, it doesn't need as much water as the ETO plant, cool season grass, needs. It only needs 50% of that water. It can thrive on 50% of the water that I would be giving to cool season grass. I can give to this plant and it thrives. That is a moderate water use plant. It has a plant factor of 50% because it's 50% of cool season grass or 50% of ETO. If I have a plant that's a low water plant, it could be 20% of ETO. And if I had a plant that was highly adapted to a condition, didn't need any supplemental water at all, it could be as low as 10% of ETO. And so that percentage that we're using there is what we call the plant factor. We assign those plant factors. And in some ways, that assignment is kind of random. And as we'll see in a few minutes, it almost doesn't matter whether we get, precise down to 10% or not. But give me a second on that. Again, in California, there's been a lot of work done on using landscape experts in the various parts of the state to come together to evaluate up to 3,500 different plants and really reach consensus on plant factors for those plants in those particular regions. So this is called WUCALS, or the Water Use Classification of Landscape Species. It's really the only state in the country that has gone to these lengths to compile this data. And it's super valuable for learning about plants and thinking about water demand of plants. In the case of California, it has been codified into a water budgeting exercise for new landscapes called the model. I know it only by its name, MWELO, what is it? Model Water Efficient Landscape Ordinance, which requires that you do a water budget for any landscapes that are designed in California, new landscapes that are designed in California. And that's becoming more and more strict, and it is actually crossing over with a general water supplier focused water budgeting approach to water management. So landscape professionals have been practicing doing water budgeting through MWELO, and now that's becoming part of water budgeting for outdoor, you know, potentially water limitations for properties in California. So it's an evolving thing, but at the heart of it is water budgeting. And at the heart of it is this assignment of plant factors by landscape professionals. And when you go to WCALS, what you are essentially doing is you put in your region. And in this particular case, you can see here, we put in region 3, Rancho Santa Margarita is representative of that. And the database allows you then to select, well, what kind of plants do I want? Do I want moderate water plants or low water plants or very low? And remember, just in your head, having heard the last few slides, if I say a plant is a moderate water use plant, what do you think right then? I hope you are thinking 50% of ETO. That's my plant factor, 50%. If I say very low, I'm thinking, yeah, my plant factor could be as low as 10% of ETO. So we put in that data, and up pops a list of plants in that particular region that meet our requirement of very low water requirement. And so it's a wonderful search tool to be able to start to put together plant palettes. And then also to do sort of a reverse check, where if you've done a design and selected plants, you can then go to the WCALS database and figure out in the place where you're building that landscape, is this plant very low, moderate, or high water requiring? And so therefore, you see here that the plant factor is less than 10%. So 10% of ETO, less than 10%. That is the plant factor assigned to a very low water plant in this particular region. Looks like agave americana here, very low, 10% of ETO in the Santa, I want to make sure Santa Margarita, yes, Santa Margarita area. Okay, that's how you use CIMMYS, and you get the idea now. It's a percentage that's assigned. There's another way of estimating plant factors, and this is actually a way that kind of the rest of the country is doing outside of California. It's a standard that has actually been adopted by the American Society for Agricultural and Biological Engineers. It's being used in water management, not just water supply management, but also in water quality management. And so it's kind of becoming a standard, a parallel standard, as I said, outside of California. And this is called the slide method for estimating water demand, the simplified landscape irrigation demand estimation. And it allows for an estimation based on sort of uniform plantings of landscapes in urban areas. It allows for estimation of water demand for existing landscapes. And it also kind of recognizes that in certain conditions, water stress may be just fine for plants. And I think this is something that the WCALS method, where we get really precise on the individual plants, there's an emphasis on the plant quality and growth and appearance of that individual plant. Okay, slide is saying, you know, we have some tolerance for plants looking a little stressed in the summertime, right? In summer dry areas. It also recognizes, and this is why I've highlighted it here, that density of planting and the number of transpiring leaves is actually more important than the minimum water demand of a particular plant. So that's going to come into play in a little bit, but it's a lot more forgiving. Slide is a lot more forgiving. Um, and I will be honest with you, I first heard of Slide about 20 years ago, and 20 years ago, yeah, something like that, and have been kind of following it. And at the time, what I understood was that a huge regression analysis had been done on plant factors and estimates of water demand, plant water demand, in a lot of regions. And this huge regression analysis got done. And what it concluded was, you know, there's not a lot of difference between a 30% plant factor and a 50% plant factor, or even a 20% and a 50%. We're talking about such small numbers that it's not really significant, this difference. And so these variations that are indicated by WU calls are maybe too precise. And for wide use of water demand. And it's kind of important that everybody start using water budgeting. So let's make it simple. And we're still not only in the ballpark, but actually maybe even getting at actual water demand a little bit more effectively than we would if we're looking at individual plants. So I'm sure there might be a question or two on that. And we'll talk about that in a bit. But the slide rules, there are 4 slide rules. You can look all this up. And basically it comes down to what I just said, that if you are measuring ETO in these large uniform turf areas, and you're comparing a turf area of this uniform monoculture of grass with other uniform monocultures of grass, that's absolutely defensible as a measurement of plant water demand. So for turf grass, ETO is a great measure of turf the reference evapotranspiration method, and the results are accurate. That measures what's going on. Big, large area of turf grass, uniform plant, etc. When you switch to landscapes that are not uniform, or that are not turf, that have a whole bunch of different species, that maybe even have spaces between the plants, now plant factor becomes a different thing, because we're no longer measuring this uniform surface, essentially. And so what slide is saying is, let's consider density maybe more so than what the individual plant is. So let's think about, if we have a landscape that's planted, 80% of the landscape is covered with leaves. Okay, now we can apply a plant factor from the slide rules to that area, and we get a perfectly good result for how much water is going to be required by that area. If it is less than 80% coverage, which kind of hope it isn't, but if it's less than 80% coverage, now we have to go to things that are maybe a little bit more specified. Slide rules also really requires hydrozoning, because you're trying to look at plants from this density perspective. So I recommend you take a look at that. Now, here's the bottom line. All that for this chart. The slide method of estimating water boils down plant factors to just a couple. It's essentially saying that cool season turf grass is 80% of ETO. So that's cool season turf grass managed in an urban setting, and allowed to be stressed. Okay, 80% of ETO. Because remember, cool season turf grass grown for measurement is perfectly watered, perfectly maintained, plenty of water, no stress. So when we have it in an urban condition and we're stressing it, we can go to 80% of ETO. Warm season turf grass could be 60% of ETO. So the plant factor is 60% on warm season. When we get to annual flowers, we're basically talking about the same kind of water requirement as cool season turf grass, 80%. When we talk about woody and herbaceous perennials in a more humid environment, Midwest, East Coast, 70% of ETO is the plant factor that can be used to estimate the water demand of those plants. If we're in an arid environment and we have woody and herbaceous plants, we can go to 50% plant factor. So essentially, our landscapes in the arid West are going to be calculated at 50% of ETO. And if we have desert plants or plants that are really uniquely adapted to a very dry condition, so these are like our low, very low water requiring plants, 30% of ETO is the plant factor. Again, you are hearing me say percent of ETO. Plant factor is a percent of ETO. Now, before we go any further, I want to take a really quick trip back to high school algebra. And the reason we're going to do this, don't freak out. The reason we're doing this is because I'm going to show you calculations that we have taken out of various documents done by scientists and irrigation management and water demand management professionals that are created for other water demand professionals to read. They don't really help normal people do these calculations. And so what we've done is kind of reordered and reorganized information in order to help you understand what's going on with the calculations. And what I want you to understand is that where we reorder things, we are following the PEMDAS method. And what that means is we're not changing just because if we have a formula that is all multiplication or all multiplication and division, in the absence of parentheses that force us to do particular things in order, we can just make it one big long line and go multiply, 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 divide. It doesn't matter. It can be done in any order. And if we reorder the pieces to make it more understandable or easier to calculate, there you have it. So the reason I'm taking this moment is so that people who are really familiar with all what I call the stacked equations, where you have all kinds of work being done on top of a dividing line, and then you have work being done on the bottom of a dividing line, and it's like this big stacked equation. Yeah, you can make that all one line, and it works just as well. So that's what we've done. All right. Let's talk about plant water requirement and kind of put together this conversation about ETO, the reference evapotranspiration rate, and the plant factor, the percentage of ETO represented by a particular plant. This is going to give us a number, inches, again, over a period of time that a particular plant requires. And the plant, we've done it, in the conversation before this particular slide. I've been saying it and we've been kind of using it, but this is just really making it straightforward as a calculation. Plant water requirement is the reference evapotranspiration inches times the plant factor percentage. We want to make sure that we indicate, is it daily plant water requirement, weekly plant water requirement, monthly, or annual? Now, that is a plant water requirement, but in a landscape, the plant water requirement needs to be adjusted by the irrigation efficiency, because the plant requires some amount of water, but the irrigation system is supplying water to that plant, and it may not supply it very efficiently. And so if it doesn't supply it very efficiently to that plant, the plant is actually going to require more water. So we take our plant water requirement, the basic, and by the way, this thing drives, this particular formula right here drives everything in irrigation, everything, plant water requirement. Now we're going to combine it with irrigation efficiency. And we're going to determine something called the irrigation water requirement over a period of time. So let's do this quick little plant water requirement. Really going to toss it off because I think you're with me and maybe even a little bored. So the July evapotranspiration rate is 5.4 inches if my plant factor is 30%. To get my July plant water requirement, I'm going to multiply the ETO by the plant factor percentage, or in this case, 5.4 inches by 30%. And this gives me a July plant water requirement of 1.62 inches. That's inches per month. What plant? Yeah, I didn't tell you what plant. It's okay. It's a plant. It's a 30% plant factor plant. So this particular plant requires 1.62 inches of water in the month of July in that particular place to thrive. So now we're going to add this irrigation delivery method and the efficiency that's associated with it to the plant water requirement. And we have multiple ways that we can be delivering water. And I didn't include in here even the hand watering or oscillating sprinkler, which is my new favorite watering device. All of those are ways that we deliver water. These are automatic or programmed irrigation delivery methods. And each one of them has a efficiency not just built into the equipment itself, but also into the way that equipment has been installed and managed in the landscape. So this concept of irrigation efficiency is important. We spend more time on it when we're talking about total irrigation runtime. But just to refresh our memories about the difference between irrigation efficiency and distribution uniformity, I thought I'd take a moment on this slide. So irrigation efficiency is a much bigger picture of how efficient that irrigation is at delivering water to the plants in the landscape. We utilize irrigation auditing to determine distribution uniformity. Distribution uniformity is essentially measuring how uniform the application of the water is beneficially for the plants. So are there areas that aren't getting watered at all? Are there places where the water's running off? Are there places where there's not head-to-head coverage in spray, not emitter coverage in drip? That's distribution uniformity. We use an irrigation audit in order to determine, distribution uniformity. Good distribution uniformity is absolutely necessary for good irrigation efficiency. Without good DU, you can't have good IE. In some cases, especially in the total irrigation runtime discussion, we'll use irrigation efficiency and distribution uniformity interchangeably, mostly because it's sort of a shorthand. DU is a big driver of irrigation efficiency. But irrigation efficiency is also about, is the equipment manufactured properly? Has it been installed properly? Is it maintained properly? Is the water being managed? So are you managing your controller? And are you actually trying to reduce runoff, minimizing loss? Are you trying to reduce loss out of the root zone? In other words, you're watering just the right amount, not overwatering where water is being lost in the root zone. So these factors are all contributing to irrigation efficiency. When we talk about irrigation efficiency, though, really distribution uniformity is a big driver and a proxy for it. So irrigation efficiency really can never be 100%. So it's important for us to think about that just for a second, because there's no irrigation that is 100% efficient. Just doesn't compute. And that's actually a very true statement. No irrigation is 100% efficient. In other words, if you don't have an irrigation system, that is a 100% efficient system. So the thing about irrigation efficiency is that every time you choose to use an irrigation system to apply water to your landscape, you are automatically having to apply more water to make up for the fact that the system is not 100% efficient. So what I mean by that is, if I have an irrigation system that's applying water to a landscape, and let's just say it's 50% efficient, just for now, that means that half the water that's coming out of that irrigation system is making it beneficially into the landscape for the plants. That means that the plant that requires X amount of water is actually going to need to receive 2X of that water in order to get all the water it needs, right? Because the irrigation system is only delivering, it's putting out lots of water, but only half of it is actually benefiting the plant. So the amount of water that needs to be applied is going to be twice the amount if it's a 50% efficient irrigation system. So when we talk about irrigation efficiency, we are always dividing by irrigation efficiency, because it's essentially increasing the plant water requirement. And when we use this term irrigation water requirement, we're essentially saying the plant water requirement in an irrigated setting. That's the irrigation water requirement. We take the plant water requirement that we calculated, ETO times plant factor, and now we're saying, with this irrigation system only being 50% efficient, I'm going to take my plant water requirement, divide it by 50%, and this is going to tell me that I need 2 times the plant water requirement in order, that's my new plant water or my irrigation water requirement. This is something you kind of have to practice with. Again, we talk about it a lot more in total irrigation runtime. What I think is important to understand here, just from seeing the formulas in the workbook and also on the screen here, is that you will see this irrigation efficiency paired with plant factor, because they're both percentages. And if you understand that irrigation water requirement is plant water requirement divided by irrigation efficiency percentage, you can kind of reorganize that formula to either be plant water requirement divided by irrigation percentage, which is just ETO times plant factor divided by irrigation efficiency, or you could make it ETO times plant factor divided by irrigation efficiency. So both of those formulas are equally valid. It's up to you how you want to use them. We're going to be seeing the highlighted one more as we go forward with building up our landscape water budgeting numbers. And so I want you to become familiar with that and not think, what the heck is all this stuff? Now suddenly I'm seeing ETO and blah. Well, look, irrigation water requirement is just my plant water requirement. What's plant water requirement? It's ETO, reference evapotranspiration, times the plant factor. That tells me how much water the plant requires in this particular place. But now I have an irrigation system, so I'm dividing by my irrigation efficiency, and that whole thing, my irrigation water requirement, describes the water requirement of this plant in this particular landscape, in this climate, with this irrigation system. So we're going to be seeing that it's more elegant, to be thinking about the percentages kind of off to the side with a little parentheses around them. Plant factor divided by irrigation efficiency makes it a little bit more elegant, but it doesn't change the outcome of the calculation. So let's give it a whirl. We had calculated a couple slides ago that we had a July plant water requirement of 1.62 inches. If my irrigation efficiency is 70%, what is now my July irrigation water requirement, or really the water requirement for this particular plant in this landscape? I simply take my July plant water requirement and I divide it by irrigation efficiency. So I'm taking 1.62 inches and dividing it by 0.70, and I come up with 2.31 inches. In the month of July, this particular plant with this irrigation system, with this irrigation efficiency, requires 2.31 inches of water per month. And the reason, okay, just point this out here, the reason that my plant water requirement is less than my irrigation water requirement is why? It's because I'm irrigating with an irrigation system that is not 100% efficient. I have to apply more water to this landscape to get this 1.62 inches there. I'm actually going to have 2.31 inches applied to the landscape. So irrigation water requirement is always more than plant water requirement. Now, in the world of water budgeting, there is a phrase that is used for both determining the budget and determining whether or not your plan meets the budget. The term is called evapotranspiration adjustment factor, or ETAF. And it's what it says it is. It's this little piece that I pointed out earlier of the plant factor divided by the irrigation efficiency. Just think about it. Plant factor adjusts ETO, and irrigation efficiency adjusts ETO. So we've taken them, we've pulled them out. Plant factor percentage divided by my irrigation efficiency percentage is my evapotranspiration adjustment rate. This allows me to start doing some formulas where I have an ETO that I set for a particular area, and now I can start making changes to the plants that I have in the landscape and the type of irrigation that I have in the landscape, and I can start to see what is the effect on the amount of water the landscape requires. So this is as I mentioned before, kind of elegant way of isolating, the plant selection and the irrigation selection. These are the things that are going to change in my landscape for the most part, and I can kind of pull them aside and start looking at them separately. This evapotranspiration adjustment factor, ETAF, we're going to use it in setting the budget, and we're going to use it in determining whether or not our plan meets the budget. But I want to start with setting the budget with an ETAF. And so the ETAF is, when you see it in the budget, you're not going to see it really broken out by plant factor and irrigation efficiency. It's just going to be one percentage. Yeah, and I'm taking a little detour before I come back to this, but yeah, so just keep that in mind. Evapotranspiration adjustment factor is essentially a plant factor divided by irrigation efficiency. All right, now this little detour is necessary so that we can start to move from talking about water in inches and move into water in gallons. And the thing that makes us able to talk about water in gallons is when we add the effect of the square footage that we're applying the water to. If we're just applying water to one plant, it's inches all the way. That's total irrigation runtime. That is irrigation management. But when we're talking about water budgeting, we're talking about a particular landscape area. We're talking about square feet of landscape. How much water does this total square footage require over a period of time? And so we need to now convert our calculations from inches into gallons. And the way that we do that is by multiplying our inches of water by 0.62. 0.62 is a conversion factor. It's 0.62 gallons per inch per square foot. Okay, so this is converting inches to gallons. Now, here's the thing. This is not relevant if you do not have square footage. Gallons are not relevant without square footage. So keep that in mind. That's why we talk about the gallons here for water budgeting, and we use this conversion factor in water budgeting, but we don't use this conversion factor in irrigation management. So the question is 1 inch of water covering a square foot. So we have a square foot, it has 1 inch of water on it. How many gallons is that equal to? Well, that 1 inch of water is equal to 0.62 gallons per square foot. And so we're going to start adding this 0.62, not adding, but multiplying by 0.62 at the end of our formulas so that we can convert all of our wonderful calculations into gallons and compare them. Now, here's an example that we can just, again, pretty quickly do. There's a reference in your book. And this is basically, the question. In a particular month, we require 3 inches of water per square foot of planted area. How many gallons does it represent? Well, it's going to represent, for 1 square foot, it's going to be 3 inches times 0.62, or 1.8 gallons per square foot of landscaped area. If I have 100 square feet of landscaped area, it's going to be 186 gallons. If I have 1,000 square feet of landscape area, it's going to be 1,860 gallons. So, yeah, this is the next step here, is to turn things into gallons. And we are done doing review. We're going to go now into new territory. All of the stuff that we just talked about is really part of total irrigation runtime calculation and irrigation water management. Now we're going into landscape-based calculations, budgeting, determining whether our plan meets that budget, and it's all based on those just couple calculations I just showed you. There really isn't very much new. It's just arranging it and thinking about it slightly differently. We'll take a break in just a few minutes. So the question for water budgeting, what you're really asking when you ask, what is the outdoor water budget? What you're asking is, how much water does a landscape require in this place? We're saying this landscape, not the landscape over there, but this landscape, which is in a particular climate area, it has particular plants in it, and it has a particular irrigation system in it. The budget for this area, this landscape, is going to be different. It's going to depend on where it is, because that's going to tell us about my climate. It's going to depend on the size of the landscape, obviously. It's going to depend on which plants have been selected, and it's going to depend on which irrigation delivery system we've selected. So if I wanted to know how much water this landscape required, I would start by asking myself 3 questions. And this really, truly is how I personally do it. I cannot tell you how many meetings I've been in where I've been standing with a group of people from all different agencies and uh, backgrounds, talking about the amount of water that we're going to budget for a landscape or that a landscape requires. And I've been able to bang out a number that's pretty darn close just by asking these 3 questions. And here it goes. The first question I ask myself is, how big is this landscape? Because for the most part, that's not going to change. This is how large is the area that is covered by landscaping. In general, this is not the area that's covered by hardscape. Uh, you know, we'll talk a little bit about that when we get into selling, but when I talk about how big is it, it's the landscape area. It's the area that requires water or that is covered by plant material. And I calculate the square footage of that particular area. So, it's 1,000 square feet. I can look around the landscape and say, yeah, it's about 1,000 square feet or it's 2,000 square feet. Okay. How big? That's the first question. Because once you answer that, you kind of put that to the side because that doesn't really change very often. The next question I'm going to ask is, well, where are we and what describes where we are? Well, for landscape industry, we've talked about the thing that describes where we are. It's ETO. ETO tells us, hey, the climate in this area is this, and it tells us what the reference plant requires in water. So this is essentially, something that I developed this skill over time, but I know, ETO is going to be different at the beach or inland or in the mountains, in a desert area, in a area that gets lots of rainfall and cloud cover. It's going to be different in all these areas. I know my area. I'm able to come up with my ETO. By the way, if you are a landscape professional, it's really good to have ETO in your back pocket, like just a general one, get in the ballpark. And, it's okay if, you use 50 and it's actually 55 per year, 55 inches per year. It's okay if you use 50 inches for your quick calculations. All right. But anyway, so how big and the square footage and the ETO, these are 2 things that once you have them and you've decided on them, again, you kind of put them to the side because they are not changing. You're not moving the landscape when you do all these calculations, right? It's going to be in the same place. So ETO is going to be the same. But the thing that's going to change is is what is in the landscape. And you observe what is in this particular landscape. And when that question, what's there, is asked, what we're really saying is, how do we describe, using plant factor, the plants that are in this landscape? And how do we describe, using irrigation efficiency, the irrigation system that's in this landscape? So we know, pretty quickly, am I looking at plants that are drought adapted plants, or am I looking at plants that are not drought adapted? Are they woody or are they annuals? Tender perennials. Do we have an irrigation system that's a drip irrigation system, obviously well installed? Do we have a spray system here? And is it an old system or is it a new system? We can make those assessments really super fast in the field and come up with plant factors that describe the plants, right? Especially using slide. If I'm in an arid environment, 50% plant factor. If I'm in a more humid environment, 70% plant factor for woody plants. And if I look at my irrigation systems, I see an more efficient drip system. Yeah, 70, 80% efficiency. If I'm seeing a really old spray system, 50%, maybe less, but 50% is bad enough. Right there, I have all the information I need to be able to tell you how much water this particular landscape requires. Essentially, I can tell you, I can start the water budgeting process. And so calculation-wise, all we're doing is we are applying our irrigation water requirement to the square footage and converting it to gallons. So we calculated our square footage. We determined our plant water requirement, which is ETO times the plant factor. We determined our irrigation efficiency, so we divide by irrigation efficiency. I now have my irrigation water requirement multiplied by my square footage. And then I just convert it to gallons, and bada bing, I have a landscape water requirement. Landscape water requirement, that's the language. The landscape water requirement is just the irrigation water requirement times the square footage of the landscape converted to gallons. If we want to write it all out so that we can follow everything, we're saying square footage times ETO times plant factor divided by irrigation efficiency times 0.62 to convert to gallons. Another way of looking at this, and a way you're going to see it sometimes in regulatory documents, is it's square footage times ETO times ETAF. Remember what ETAF is? It's the ET adjustment factor. It's just plant factor divided by irrigation efficiency, or it's been given to you. So here's how we apply it. In this particular case, we have a plant which is a cool season grass that is not maintained, is maintained exactly like ETO. So in most cases, we would apply an 80% plant factor to cool season grass because we're allowing it to have a little bit of stress. But in this particular case, we're saying, no, this is a 4 to 7 inch, beautifully grown, blah, 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 cool season grass. And its water requirement is 100% of ETO. The ETO is 45 inches, 100% of ETO, 45 inches. That is the plant water requirement for this particular plant. For the moderate plant, we have 50% of ETO or 23 inches required. For the low water, 9%, and for the very low, 5%. And now we want to put that all kind of together and come up with the landscape water requirement. What do we need? We just figured out the plant water requirement. What we need is irrigation efficiency, and we need the square footage of the site. I'm saying it again here on this slide because I cannot tell you how many times we have had pushback because a lot of the regulatory documents put the square footage in different places, or they put the ETO in different places in the formula, or they put the ET adjustment factor in different places, and it doesn't matter where it goes. The way we do it is square footage because how big is the area doesn't change. ETO, that doesn't change. Plant factor and irrigation efficiency do, and then multiplied by 0.62. So I'm just repeating that here. Now we get to talk about the fun part. This is, again, this is really how I use landscape water requirement, which is the fundamental equation for all water budgeting conversation, outdoor water budgeting conversation. This is how I use it in my daily work and working with clients. Once you get this landscape water requirement formula down, you are going to be amazed at how easy the rest of it is. I mean, it's almost too simple after that. So landscape, it's worth spending one more slide to hammer it home. Landscape water requirement in gallons is square footage times ETO times plant factor divided by irrigation efficiency converted to gallons. And basically this is just how big is the area times where am I as described by ETO inches times what plants are there, percentage plant factor, divided by what irrigation efficiency percentage, times 0.62. And that's it. So if you are following along in the workbook, go ahead and turn to page 14. We're going to do a just very quick, this is like what I call muscle memory, mental muscle memory, calculations. It's going to bring up some issues for us that we can think about. But again, it's really just practicing using this landscape water requirements calculation. And so for all of what we're going to do in the next few slides and on page 14, we're looking at an annual ETO. Just make sure that that's the case. Yes. An annual ETO of 47 inches and an irrigation efficiency of 75%. And so the first thing that we want to do, and just really take a couple minutes to calculate the landscape water requirement for cool season grass using the slide method and WUCALs. What do you come up with? Well, I'm going to do this one with you because the answer is the same whether we are using the slide method or WUCALs. We set up our landscape water requirement formula by putting the square footage, which is what? It says there in the title, 1,000 square foot landscape. And then what's the next thing? Where are we? Well, that's annual ETO of 47 inches. And then the question is, what's there? What plants are in this landscape? And it's described by plant factor percentage. Under the slide method, cool season turf grass is 80%. And so that's our plant factor. And then we are given our irrigation efficiency of 75%. And we now have all the information we need in order to tell us how much water this landscape requires. It's going to require 31,083 gallons per year. This is the landscape water requirement using the slide method for determining plant factor, 80% plant factor, 75% irrigation efficiency. In this particular place, 47 inches ETO, 1,000 square foot landscape. Hey, a 10,000 square foot landscape, just multiply this by 10. Easy. Okay, now if we use WUCALs, what does that tell us? Well, it turns out that on the cool season turf aspect, WUCALs and slide method agree. The plant factor is 80%. So there's nothing different here. We should come up with the exact same number of 31,083 gallons per year. Okay, very straightforward. We've now, if we think about this little exercise, this is basically what water suppliers are doing to try this calculation. They're doing this in order to try to have us think about removing the cool season grass and replacing it with landscape covered in some other plant material. And so in this particular case, we've selected lavender as our plant material. And this is where we're going to start to see some slightly different information, because we're still, how big is the area is still the same. It's 1,000 square foot area. We haven't changed the landscape, so it's still in 47 inches annual ETO. But now the plant factor is going to change. If we use the slide method, the plant factor is 50% because this is a woody plant in an arid climate, an herbaceous perennial or woody plant in an arid climate. So 50% is my plant factor. If I go ahead and do the calculation, again, my irrigation efficiency being 75%, I find out that my landscape water requirement is 19,427 gallons per year, covering the same square footage with just the lavender and calculating it using the slide method. If I utilize the WUCALs method, I am going to see a slightly different number. And that's because WUCALs is telling me that the lavender is a low water requiring plant. putting its plant factor at 20%. Now, it could be 30%, it could be 10%. That's the art of WUCalls. It's okay. If you are in need of that kind of specificity and knowledge, wonderful. I'm picking the middle between 10% and 30% and assigning that to the lavender in this particular place. So now my plant factor is 20%. What happens to the landscape water requirement when I change the plant factor? I haven't changed the square footage. I haven't changed the ETO. I haven't changed the irrigation, but I've changed the plant factor. And now I have a landscape water requirement of 7,771 gallons. This is a big difference in water requirement, or what I am thinking my landscape water requirement is going to be in each of these scenarios, using the two different plant factor estimation methods. And we're going to talk more about this at the end, but beside the fact that I've used two different plant factor methods, what we've also demonstrated here is that when we change the plant factor, our landscape water requirement changes. And we can start to use this to make choices about plants, to make choices about the landscape areas that are going to be covered by a particular plant. And this is really sort of at the heart of this type of just repetitive landscape water requirement calculating is kind of at the heart of selling the idea of removing grass and replacing it with landscape. Because if you stick with the slide numbers here and compare the cool season grass with the plant factor of 80% at 31,083 gallons per year, and you say, okay, I'm going to remove that. I'm going to replace it with a plant lavender, which is only going to require 19,472 gallons of water per year. I can make the case that I'm going to save you 11,611 gallons per year by replacing that cool season grass with the same landscaped area with lavender. Why? Because it has a lower plant factor. And again, this is the essence of turf removal and replacement projects right here, landscape water requirement calculations. It's a powerful calculation. And you can actually use this to impress your clients and sell your services to other people. I'm going to show you an example of how I did that. And this is going to be on page 16. This is a real site. And I want to take just maybe 5 minutes for you to go ahead and start to think about answering these questions. But answer that first question. What is the original landscape water requirement? So that's the scenario on the left side where you have a total landscaped area of 50,000 square feet, an annual ETO of 49 inches a year, and mixed season turf grass of 80% plant factor, and an inefficient spray irrigation of 50%. Go ahead and answer that. What is the original landscape water requirement? And this is maybe a little bit of a better picture. My first question, of course, is how big is it, right? And what's there? So I'm just making sure that I understand. It's mixed season grass. That's 80% plant factor. According to the slide rules, my irrigation efficiency is really crappy, 50%. I mean, it's probably worse than that, but I'm giving it the benefit of the doubt at 50%. So the one thing I know, by the way, just looking at this, is that if my irrigation efficiency is 50%, I'm going to need twice as much water for this landscape to make it happy and healthy. So I already know that my landscape, my irrigation efficiency is something I could improve very quickly and have some effect immediately, pretty much, on how much water I'm going to be utilizing at this site or how much water I plan to use at this site. And the house is being built. So why don't we go ahead and make a change to the irrigation system? And so if you're following along with the workbook, we're asking this question here. What happens if we change out those irrigation nozzles? But first, I'm sorry, let me go to answering the question. The question is, how much water does this original landscape need? Well, the original landscape is going to need 2,430,400 gallons of water per year. For that, I mean, honestly, 2 million gallons of water, 2.5 million for that? Okay, I already know with that really crappy irrigation efficiency, I can change it out. So what happens if I change that irrigation efficiency to 70%, which is in your book? Go ahead and do that calculation. Plug in, we haven't changed the plant, so it's still mixed warm and cool season grass at 80% of ETO, right? The plant factor is 80% still, but I'm going to change that irrigation efficiency. And you can see in the workbook, it says I'm going to change it to something with a 70%. So that's like a rotating nozzle, right? A multi-trajectory rotating nozzle, 70%. And I could maybe even get better than that with those, but 70% is an upgrade. Not too difficult to do. It's basically a nozzle replacement. I'm going to do it while the house is being built. Okay, has everybody done that? They've redone this calculation using the 70%. And so what do you get? Well, you get that the new landscape water requirement is 1,736,000 gallons of water per year. You've saved almost 700,000 gallons of water just by making that very quick nozzle replacement change, a worthwhile change, more efficient. So the irrigation efficiency is affecting the landscape water requirement by saving you 700,000 gallons. The next step is what happens. So now, we've had some time to redesign. What if we change out our plants? And we change our plants. I know it says here, this is actually a little mistake. It says here that the native plants on the screen, it says 10%, but we're going to stick with the slide rules. So we have a plant factor of 30%. So if our plant factor is 30%, and we're sticking with our new rotating nozzles at 70%, what's the new landscape water requirement? Go ahead and plug it in. Still, how big? 50,000 square feet. Still annual ETO of 49 inches. But now my plants have changed. I'm changing them out for these native grasses and shrubs with a plant factor of 30%. They're really adapted to this arid condition. And I have this new irrigation system at 70% irrigation efficiency, and then I convert it to gallons. Do you get that the new landscape water requirement for this landscape is going to be 651,000 gallons of water per year? Okay, what have we just demonstrated? Well, we've just demonstrated that new design is going to save almost 2 million gallons of water a year on this landscape. At least that's what we estimate it to be, right? We could manage it so that it doesn't, huh? But our estimation of the amount of water this new landscape is going to require is going to save us about 2 million gallons a year. And you know what that is? Especially when you're talking to a client like this, who needs numbers to be able to make investments. I call that boom. I call it boom. Because when you lay down a piece of paper in front of a client and you've just done on the back of an envelope, essentially a calculation that shows them that they can save almost 2 million gallons of water a year, I don't care how well-heeled that client is, or if they're a commercial client, or if they're a residential property, people are going to take notice when you show them the real numbers that you are using in order to plan the water use for the landscape. This landscape water requirement calculation is really, I think, the most powerful tool in the toolbox for designers to have, and for landscape contractors to have, because you can look at designs. You can, and if you're doing design build, you can be talking to clients. But if you're just doing build and you look at a design and you don't see that you're having this kind of saving and you're not able to justify that in your own head, this is something to talk to the design team about, because you understand that they are trying to make changes in order to save the water. And if you essentially catch it out that it's not doing it, this is a valuable contribution to a team and to ultimately to the value of the project. So whether you are in the design phase or the construction phase or the planning phase or the regulatory phase, landscape water requirement is, I think, one of the most powerful tools we can have in landscaping. So now let's put this in the context of water budgeting. In water budgeting, we have to first ask ourselves the question, before we can set a water budget, we have to ask ourselves, well, what is the maximum landscape water requirement of this site? And that's easy, because the maximum landscape water requirement would be 100% of ETO. That's kind of as much as they would need. Actually, the maximum really truly would be almost 200% of ETO if you included an irrigation component to it. But 100% of ETO is where we're going to start, because that's saying, hey, if you could have all the water as efficiently as possible, and plants that require the maximum of ETO in this landscape for the whole landscape, how many gallons is it? What does it convert into? Well, it converts into essentially 100% of ETO. This is the maximum amount of water that you could be putting on the landscape. But I don't want to be putting 100% of ETO on these landscapes. Landscapes actually don't need 100% of ETO. This is like a sort of, dialogue that's been created by the irrigation world. We don't want to be applying 100% of ETO to the whole landscape. We want to set a budget. We want to say, well, some percentage of that should be allowed. But what is it? Is it 50%? Is it 80%? Like, how much of that water are we going to allow people to use in the landscape? And the process of setting this boundary, this budget, is called creating the maximum applied water allowed, the MAWA. It is actually budgeting. It's saying, hey, you could do 100% of ETO, but we're not going to let you. We want you to do some percentage of that. So we want you to reduce your landscape water requirement to the maximum applied water allowed, or to the budget. And good guidance for percentages that we can reduce the landscape water requirement to are as follows. Single and multi-family residential projects could be reduced to 55% of ETO. Non-residential projects, commercial and so forth, could be reduced to 45% of ETO. If you have a special landscape area, and we're going to talk about that in a little bit, you might be allowed to keep that 100% of ETO. A special landscape area could be like an edible garden, let's say. It's a worthwhile use of water in that edible garden to use it at 100% of ETO. We'll talk about special landscaped areas in a bit. Let's focus on the ones on the adjustments that are tightening the budget. So these percentages here that I've called out, the 55% and the 45%, these are called the ETAF, the ET adjustment factors for the landscape water requirement. And we're going to go through a little example of this because you're going to get it right away. I mean, again, it's the same formula we've been using. If I were allowed to use all the water I wanted here, what would be the 100% of ETO landscape water requirement? Well, it's a total area of 1,330 square feet. That's how big it is. Where are we? 49 inches of ETO per year. And my ET adjustment factor is going to be 100%. So I'm going to multiply my square footage by my ETO by the adjustment factor of 1.0, convert it to gallons, and I come up with 40,405 gallons per year if I could have 100% of ETO. But I want to budget this. This is a commercial landscape. I want to tighten the belt and only allow you to have 45% of ETO. My new ET adjustment factor is 45%. And so I'm going to I'm reducing the water use by 55% in doing that. I want to know, what is my new landscape water requirement given this budget of 45% of ETO? And I'm just going to go back to my landscape water requirement calculation to come up with my new water budget calculation. It's how big is it? 1,330 square feet. It hasn't changed. It's still in 49 inches per year ETO. But now my ET adjustment factor is 45% or 0.45. I'm going to convert it to gallons. And I find out that I'm only going to be allowed to have 18,182 gallons of water per year for this site. Wait a second. 100% of ETO says I can have 40,000, but you've just put me on a budget that says I can only have 18,182 gallons. This is the budgeting process. It is applying that ET adjustment factor to the landscape square footage to come up with the maximum applied water allowed for this landscape. The MAWA is the water budget. And in this particular case, it is reflecting a 55% reduction because we are only allowing 45% of ETO for the water for this site. Now, the question is going to be, can I actually design a landscape that only is going to use 18 or require 18,000 gallons a year? That's the question. And we need to determine whether our budget is going to be exceeded or met by this designed plan that we are coming up with. Now, I mentioned that special landscaped area earlier, and I'm just going to come to it again because special landscapes affect both the water budget and our designed water plan. When we say that a landscaped area is special, this is in particular like an edible area or a sports field or some place that is specifically designated as a place where it's a beneficial use of water. I mean, I think all landscapes are a beneficial use of water, okay? But this is a beneficial use of 100% of ETO. Like, it can get all the water it needs. We're not going to stress it. And those areas are designated as special. They are called special landscaped areas. We're going to allow them to have 100% of ETO. And basically, when we do both our budget and our plan, we are going to carve out the square footage that is devoted to the special landscaped area, and we're going to allow it to have 100% of ETO. The rest of the landscape is still going to be subject to the ET adjustment factor. So like in the last slide, that was 45%. The rest of the landscape gets 45%, but the special landscaped area can get 100%. When we are conveying our total budget for the site, we add those two areas together. This is something that we're going to do Also in the design water plan, this is the essence of hydrozoning. I'm bringing it up now just so you understand that it is something that we are going to have to take into consideration. So if we have, this is a just for fun little, jaunt through special landscaped areas. But if I had, that landscape that we had, and it turns out that we actually did put a vegetable garden on a quarter of that landscaped area when we did the design. But if I take that landscape that we just looked at with 1,330 square feet total, and I said 25% of it is going to be special landscaped area. The rest of it is the usual deal. I have to break that landscape into two sections. One is 25% of the total area, so that's 333 square feet. That's my special landscaped area. And then I have 997 square feet is the other part. I am going to apply two different ET adjustment factors to these two different areas to get my new water budget. This is so in this so actually this actually has a little bit of a change in it too. This is saying that this is what you get for having to do lots of examples and just trying to change some things. They don't always tally up, but you will note that I made the ET adjustment factor 55% here, which would be more indicative of a residential site than a commercial site. Let's go with it because I think the numbers actually do tally out. I think the numbers tally out. Yes, they do. So this is basically showing us that for the special landscaped area, I am able, this is my landscape water requirement formula. I'm taking that special landscaped area of 330 square feet. I'm multiplying it by 49 inches ETO times 100 ET adjustment factor, converting it to gallons. I get 10,117 gallons. On the rest of the landscape, I'm going to apply the ETAF of 55%. And that is going to give me 16,000 gallons. I add the two together to get my new MAWA, my new water budget, maximum applied water allowed. Okay. Great segue for the next step because the water budget is pretty straightforward. And now the question is, can we design something that actually meets or is less than the water budget? And in order to do this, we need to be reminded that in nature, plants naturally group themselves by their communities. So we have plants grouping themselves by water need, by soil type, by sun exposure. All of these are ways that plants will group themselves. And I might add that you're not going to see the same plants grouped together on the side of the hillside, exposed to all the elements and wind and so forth. You're not going to see those same plants grouped the same way down at the bottom of the hill under trees, right? Two completely different situations. And when we design our landscape, we need to think about plants grouping in a similar way, especially if we're going to irrigate them. So hydrozoning is a irrigation concept. It's basically zoning the plants for water, hydrozone. And we are grouping plants in our designs that have similar water needs, similar sun requirements, etc. And so in a landscape, we can start to break that landscape apart into different water needs. And that's what we've done here. So here we have two different hydrozones in the landscape. We have one hydrozone, which is lawn. This is a high evapotranspiration, plant factor of 80%. And we have low evapotranspiration plants, Mediterranean plants, woody plants, arid setting, 30%, highly adapted, 30%. of plant factor. These two things cannot be irrigated the same. They are completely different water requirements, and so they need to be viewed as two separate zones in the landscape. And also, you can have zones that are, and it's interesting because I use this as an edible garden, and that should probably be a special landscaped area, but we're going to get away with it in this analogy here. You can also group, make zones based on the type of irrigation that they have. So if you have an area they're the same plant factors, but you have an area that's being irrigated by spray and an area that's being irrigated by drip, these need to also be separate water zones because they're going to have different irrigation efficiencies. They're going to be, certainly for timing of your irrigation, this needs to be different. But in terms of determining the amount of water that you're planning to use in that area, you're going to need to keep them separate. So hydrozoning, first and foremost, by plant factor, then by irrigation efficiency. And essentially reminding you that, the more hydrozoning you do, the better for managing your water. The easier it is to manage your water. And you can group these plants by a lot of different things: plant factor, sun exposure, irrigation type, soil depth, size of plants, all your trees and shrubs together, all of your ground covers together, soil type, lots of different ways you can do it. Plant factor being sort of the number one thing. And when they're irrigated, you're going to devote an irrigation valve to each of these zones if you can, because that control of the application of the water to that zone is going to help you to manage your irrigation to your water budgeting. So hydrozoning is absolutely essential if you want to have efficient irrigation. The two go hand in glove. If you have plants that have mixed water requirements, that are drastically different, and you're trying to irrigate that thing, somebody's always going to be unhappy. So hydrozoning is something you really want to be thinking about. And essentially, what you're going to be doing is taking a design and now breaking it into the hydrozones so that you can evaluate the water requirement for that particular zone and compare it to the budget. So in this particular case, we have three main hydrozones. We have the very low water hydrozone along the driveway. We have this kind of low water hydrozone that's, wrapping around and through the property. And then we have actually two, we can add them together, moderate water hydrozones that are utilized, are more in the rain garden area and under trees and shade and so forth. What happens if you have a hydrozone that happens to have a mix of plants with different water requirements? What do we do then? Well, in that case, it's best to err on the side of higher water use or planning for higher water requirement. And so what you do is you find the plants that have the highest water requirement in that zone and then make that zone entirely a high water requiring zone. This is a conservative way of estimating your hydrozone water requirement. Essentially the landscape water requirement for that particular hydrozone. The most conservative way to do it is to find the highest water use plant in the zone. If you're using a WUCALS or other really like designated plant approach, if you're using the slide method, this doesn't totally apply because there's it's a lot of this plant factor is very generic. What do you do if you have a water feature as a hydrozone? Like maybe you have a swimming pool that's in the landscape or a very large fountain of some kind. How do you describe that in the hydrozone, landscape water requirement? You're figuring out how much water that hydrozone requires. What do you do with a swimming pool? Well, in a swimming pool or in a big water feature, the adjustment factor that you are going to apply to that area is 100%. In other words, you're going to describe this as a just evaporating, thing. Irrigation efficiency doesn't really apply here. We don't have irrigation, but this is a thing that uses water. And so it needs to be included in our plan, and describe the landscape as planned. It is definitely separate from an area that's covered in plants. And so it's going to be assigned 100% of an adjustment factor. Now, this is important to remember because we're using ET adjustment factor in a lot of different ways. This is adjusting the ETO in your hydrozone water requirement calculation, the landscape water requirement calculation for this particular zone. This is in the plan phase. This is not in the budget phase. In the budget phase, you don't get 100% water for this. You only get the 100% for an SLA, for something that is like really a special use of water, good use of water. Swimming pools don't get extra water in the budget. You're going to have to work it out if you have an area that is a swimming pool, because it's going to require 100% of ETO. What do you do if your hydrozone doesn't require any water? So this is interesting. In most of the regulatory calculations, for example, with the California Model Water Efficient Landscape Ordinance, you actually remove that square footage from both the water budget and from the water plan. So from both the MAWA and the ETLU. And you take it out completely if it doesn't require water. You're only calculating budget and designed water on areas that are using potable water. That said, that's regulatory. If you're selling to a client, I would keep that in. You're looking at the total landscaped area water requirement. You are telling them that you're going to reduce that water requirement by X amount. And one of the ways you're going to do that is by taking this square footage and not using any water on it. I think it's a totally legitimate aspect of landscape water requirement in this sales pitch. And I use it all the time. And I would use the same rationale for gray water, or for areas that are using gray water, or that are using rainwater for irrigation, because they're not relying on potable water. I would keep them in the total landscaped area for the purposes of talking to clients, but then I would remove them from the actual water use. Now, again, this is a difference between regulatory reporting and selling your services or selling the concept. You understand landscape water requirement, the budget, and the hydrozoning well enough to be able to be facile with this kind of stuff. So what you end up doing is taking your plan for the landscape and breaking it into these hydrozones, and then calculating the landscape water requirement for each of those hydrozones. And on page 18 of your workbook, you'll find this image with the square footage of each of the areas, and you're asked the question, what is the hydrozone water requirement of each of these areas? We don't really have time for you to do that now, but I recommend that you go back and do it, because after you have done that, you've come up with the hydrozone water requirement, which is just the landscape water requirement on that square footage. You add it all up to come up with your design water plan. So let's go back to this landscape now. Remember this project? In the commercial context, we said it's a 45% water budget on here. We're going to be allowed to have 18,182 gallons. We calculated that earlier. We've designed a new landscape. And the question is, does it meet or exceed our water budget? Well, the new landscape actually has these low water requiring plants that we've assigned a plant factor of 30% to. And we have drip irrigation that is highly efficient at 80%. Have we met our budget or not? Let's do the calculation. How do we do it? Well, we set it up as a landscape water requirement calculation. We're just calling it something different. We're calling it the estimated total water used or the designed plan. You can call it pretty, the hydrozone. There's only one hydrozone here. This is the amount of water that we are actually designing this landscape to require. We have, how big is it? It's 1,330 square feet. It's in 49 inches of ETO. But now our plant factor is 30% and our irrigation efficiency is 80%. We convert it to gallons and we find out that we've designed a landscape that only requires 15,152 gallons. This is good news. Why? Because our designed plan, our estimated total water use, is less than our maximum applied water allowed, or our design plan is less than our water budget. This is a project that would be approved. Now, what about a landscape with the SLA and water budget of 26,000 gallons per year? Well, remember we calculated the water budget where we said grass was going to be on 997 square feet and the edible portion of it was 333 square feet. Hydrozone 1 is the portion that's going to be changed out from grass to something else. We're going to calculate the hydrozone water requirement there, and we're going to calculate the hydrozone water requirement on the SLA, and we find out that the hydrozone water requirement of the converted area is going to take into consideration the new plants, 30% plant factor, 80% irrigation efficiency, and we come up with 11,358 gallons on that portion. On the edible garden portion, it's the same as what it was in the budget. It's 10,116 gallons. The total of the two is our estimated total water used for the design plan. This is our designed water plan for this landscape, 21,474 gallons. This is also approved because remember, we had a landscape water budget in this particular case of 26,776 gallons per year. Now, there are some ideas for minimizing this amount of water, and hydrozoning effectively is really the best way to minimize your more hydrozones, more careful consideration of hydrozones. You might want to think about not having, taking areas out of your irrigation scheme and turning them into either irrigated by rainwater or gray water or not irrigated at all, or even ones that are going to be irrigated just for a couple of years till established and then they're going to be out. You want to plant densely and diversely, and we'll talk about that in a second. Selecting those climate appropriate plants is super important because they have the adaptations to reduce the actual total amount used. Having the most efficient irrigation system. The more efficient your irrigation system, the less water is going to be in your design plan, right? Like, go for it. And then building living soil and capturing rainwater and gray water and so forth. Those are all really important aspects too. So how do we account for precipitation? Well, rainwater does play a role in water budgeting. And, the thought process is that it actually is going to reduce the budget itself. So rainwater is going to make it even tighter. We can tighten our belt even more if we're getting rainwater. The question is, how do we actually, calculate that? Like, do you estimate? How do you estimate the amount that you're going to apply, to the formula? And if we expect precipitation at different times of the year from when we're utilizing the water. Does that change our assumptions? Like, is that something that we need to take into consideration? For a long time in California and in other dry areas, there was the argument, hey, we shouldn't take precipitation into account if we're not getting it in the summertime to offset irrigation. Is that legitimate? And so how do we use it? Well, a formula called effective precipitation has been introduced. And this is really simple. This is basically saying, look at the previous year's 25% of the annual precipitation in inches. There's an average rainfall that is used in some regulatory uh, situations. Your particular region is going to dictate to you which rainfall calculation are you going to use. At G3, we use the previous year's annual precipitation so that it does vary, but this is for our own internal design, strategy. So effective precipitation is only a portion of that annual precipitation. It's 25% of that annual precipitation in inches. And we're going to calculate that effective precipitation and then subtract it from ETO in the MAWA calculation. So effective precipitation at 25% of annual precipitation comes up to a bunch of, different numbers depending on where you are. If you're in Denver with annual rainfall of 19 inches, effective precipitation, or 25% of 19, is going to be 4.75 inches. If you're in Des Moines, where you get 36 inches of rainfall a year, your effective precipitation is going to be 9 inches. And remember, we're going to be subtracting that from our ETO. It's going to adjust the ETO in the MAWA calculation, in the budget calculation. So if we have a landscape area of 1,000 square feet and an annual ETO of 50 inches a year, with an annual rainfall of 15 inches a year and an ET adjustment factor of 45%, what is our water budget going to be? Well, first we figure out how much precipitation are we going to take away from ETO. And we do that by 25% of rainfall, or 25% of 15 gives us 3.25. So 3.75 inches is going to be subtracted from MAWA. The MAWA calculation without considering precipitation is the square footage times the ETO times the adjustment factor of 45%. That tells us our MAWA is going to be 13,950 gallons. But if we take into consideration effective precipitation and we subtract that from the ETO, we now have a MAWA of 12,904 gallons. We have effectively reduced the water budget, the amount of water you're going to be allowed to use on this site, by about 1,000 gallons, which is representing 25% of the annual rainfall. This is kind of controversial, but I think it's great in terms of forcing all of us to be thinking about resources in the landscape. And we use effective precipitation every time. So there are a couple of examples in the book for you to play with. I recommend that you do that and just kind of see, how these MAWAs pan out. But it's a pretty simple addition to the whole thing. Now, here is the last section, and basically it puts everything on its head. Do you see how easy it has been to go through this landscape water requirement and turn it into water budget, maximum applied water allowed, or designed water plan, the estimated total water used, or my hydrozone water plan, my hydrozone water requirement, the amount of water needed for a particular hydrozone, the SLA water requirement, the amount of water needed for that special hydrozone. It's been pretty easy because it's all the same thing. And, we get really, I think, complacent thinking about landscapes as just being plants or irrigation. But in fact, landscapes are something more than that. They're also soil type. But you know what? It goes beyond soil type because, really thinking about it, soil type is probably taken into account in the ETO calculations. The slide method of calculating plant factor kind of gets at this difficulty of breaking a landscape down into plants and irrigation and saying that's how much water it's going to need. Because it starts to talk about, well, plant factors are the amount of water required by a particular plants in a landscape is affected by density. It's going to be different if it's 80% or greater coverage in the landscape. It's going to be different if they're plants isolated in the landscape. It's going to be different if it's a monoculture of plants that are all grown together. If it's grown in an urban area, it's going to be different if it's, a highly diverse set of plants in particular microclimates. All of these things are kind of gotten to in the slide method of simplifying the plant factors. And I welcome this because it more accurately reflects the science of what's going on in a landscape. Turns out landscapes cannot be reduced to simply being called the sum of plant water requirement and irrigation efficiency. That actually doesn't describe landscape water demand, in part because this assumes that we are managing a landscape for field capacity, for this just right balance of oxygen and water. In fact, all of irrigation comes down to managing a landscape for field capacity. It doesn't give us a lot of room. In general, regulatory frameworks like MWILO don't give us really very much room for stressing landscapes or for looking for what I'm going to call syntropic or complexity effects. What happens when landscapes are super complex? They start to behave completely different than when they're not complex. After all, how do these landscapes survive without irrigation? Like, how does it happen that we can have evergreen chaparral? Yeah, there's something going on here that is beyond irrigation efficiency, and it's certainly beyond plant factor. And it requires that we take into consideration that plants are actually re-engineering their landscape conditions. They are controlling their environments. They're cultivating this subaquatic system that is filled with microbial activity. And, that may be something that many water planners and landscape people kind of understand now because it's been in the world of landscape management for a while. This understanding, hey, we have to make sure soil has organic matter in it, and that there's something going on microbially in the soil. But what it doesn't really recognize is the fact that this re-engineering that's happening by plants is also managing a living system in the soil, and that living system has a feedback loop on the plant. In other words, the microbial activity in the soil is actually changing the way the plant is responding to the environment. It's editing the genes of the plant in a particular environment. It's creating heat tolerance, drought tolerance, cold tolerance, salt tolerance, all the genetic expression of a particular plant in the landscape is being controlled by the microbial community in the landscape. So yes, we can go through this process of selecting plants. We've done it mathematically. Hey, I've got grass on a site. How much water does my landscape require? I'm going to rip that out and put lavender on the site. How much water does my landscape require? We can go through that process, but we may not actually get the drought tolerance, the heat tolerance, etc., that is going to allow us to really meet those objectives when we're applying the water If we don't plan also for high diversity and high density, 80% or more of the site covered with plants. And this comes back to something that is called biological quorum sensing. This is the mechanism that the microbes in the soil are using to activate genetic predisposition of plants. When you select a plant that has a drought adaptation, you do not see that adaptation exhibit itself until the genes are edited by the microbial community. So the microbial community says, okay, turn on your drought tolerance, and then the plant expresses it. If the microbial community does not say turn on that genetic predisposition, we do not see it exhibited in the landscape. And the only way that we get this quorum sensing to happen is when we have a high density of plants and a high diversity of plants. Because the plants are creating a community, not just the players, like who is there, but also where are they living. They're living in a structured soil that the plant is actually creating, and the microbes are actually creating. They're creating a highly organic, matter filled and highly spongy type of environment, and it's happening where the roots are. If you have a plant in one part of the landscape and 10 feet away you have your next plant, it's going to take a long time for the root zones of these two plants to begin to interact. And it's that interaction of the root zones and the biology that lives on the root zones that is causing these complexity effects. So if we're not planting densely, we're not getting that root zone interaction. We're not getting this microbial benefit of editing the genes to make the landscape more, more drought tolerant, as an example, or more cold tolerant. That microbial biochemistry is helping to make a spongy soil that is able to hold on to more water. So that matters in water budgeting. I mean, we take into account precipitation, but the amount of water that's being held in the soil exceeds or is far different than what our soil type would indicate. This is structure. Soil structure is what determines whether or not water is being held in the soil. And you do not get soil structure without microbes, and you do not get microbes without root zones of plants. What is actually happening in our landscapes that are well designed, densely planted, and diversely planted is we get a water holding superorganism. The plants and microbes, the plants in the soil are working together to hold on to water and to release water, to manage the water cycling through the system, up through the plants into the atmosphere and back down onto the earth in relatively the same place where that water is being released. This green water zone management is really the essence of water management in our landscapes, and we don't really get to that with landscape water requirement calculations. It is an estimate at best, because green water resources can be massive. When we plant diversely and so forth, we can get root structures that are incredibly big. And those incredibly big root structures are where all this activity is happening, where all the water is being stored, where all the soil is being converted into a sponge. And on top of it, when the plants are able to pair with fungi in the soil, so it's become a more perennially dense system, that fungi is able to do incredible things. It can access water from other places, and it can actually access microfilms of water in the soil. So soil can become desiccated to the human touch, but it still has microfilms of water that only fungi can access. The plant roots can't access it. It's too tightly bound to the particles of the soil, but the fungi can get in there and get at that water. So I think the point here that I'm trying to make is that we're using water budgeting. It's a great broad stroke. It gets us in the ballpark. It gets people understanding, hey, landscape water requirements are important to us. We need to think about them. And at the same time, we need to be thinking about how does our management of the soil and our creation of a really dense and diverse landscape affect our design plan, affect the amount of water that the landscape actually requires. Because when we have a landscape that's dominated by fungi, the wilting point of the plant material decreases, right? The fungi are able to access water that plants can't. So also, when we start talking about effective precipitation, at 25% is nothing, because when we have soil that's like this and we have a system that has re-engineered it into the chocolate cake that you see here, this spongy, porous, but also water holding soil, we get infiltration like nobody's business. When aggregation of the soil is high, the soil takes on all new characteristics, and so when it rains, we get it all and we hold on to it all. So effective precipitation begins to become equal to the amount of rain received, not just 25%. And on top of it, this is encouraging root depth growth, right? When the microbial community is active, we're getting plenty of water from, holding on to rainwater and so forth, we begin to get a cooperative plant effect, root depths increase, fungal hyphae increase. Now we don't have to worry about irrigating at the highest water requirement for mixed borders, because the mixed borders are working, all those plants are working together to reduce the water requirement of the whole site. And so this is really something that we need to start thinking about in our landscape water requirement. And it's also going to be coming up in our conversation about total irrigation runtime. I want to leave us with the 8 regenerative principles that we are really thinking about in terms of helping to reduce landscape water requirements or meet landscape water requirements. These are the 8 regenerative principles. Key amongst them is minimal disturbance. So we're talking about landscape transformation by removing grass, disturbing a site. We need to think about that in terms of our water budget, because the landscape is always going to require more water when we have disturbed it, no matter what we're doing. Rainwater is a resource, of course, holding on to that rainwater, covering the mother, essentially making sure that there's really no evaporation, making sure that we have a real density of ground cover, keeping living roots in the soil all year long. If we're in an environment where we have a growing season that's year long, we have this tremendous advantage of building just incredible water resources in the ground in areas where we're limited by freeze effect. This is even more important to keep those plants on the ground during the cold season and only begin to add new plants in when things warm up, and edit and manage at that time, but not to disturb, to keep those roots in the ground. Diversity is going to foster all this resilience we talked about. Animal impact, I mean, in the context of us in urban spaces, this means let's get more people out playing in landscapes, not just at parks, not just at soccer fields, but in landscapes, like walking around in their own landscape. And no routines essentially means that we want to think about how we manage our landscapes for the pruning less and so forth. In your book, on page 28 and 29 are going to be 13 questions. These are questions that we can talk about now and go through, but they are indicative of some of the types of questions that you're going to see in the quiz that you are going to take. In order to get your CEU credits for this class, you need to take a quiz and complete it. And that's because it's a part of the Climate Ready Landscape Academy. It's a professional class. We want to make sure that you're understanding, and even more importantly, this becomes a class that you can use to sit for the Watershed Wise Landscape Professional exam. But you can only do that if you take the quiz and get your CEUs. This website, Watershed Wise Training, is going to take you to a site where you'll find this class, and you click on Start Learning after you register. And in this class, you can watch this workshop again, the video of it. You can also do some other exercises that are there. The workbook is there again, if you want to print out more. It has a whole lot of information, and it has the quiz. And you just click on Start the Quiz and take the quiz. You have to get 8 out of the 10 correct in order to call it passed. You can take it again. That's the best part. You have you have 10 attempts to get 80%. I think you can do it. And it will show you your answers. It's great. And you need to do this anyway if you're going to sit for the Watershed Wise Landscape Professional exam. The Watershed Wise training is also available on the Watershed Wise website. And this is the whole professional certification. You can just skip all this Climate Ready Landscape Academy stuff and go straight to taking it online. That's a great way of doing it, but we will count this particular class along with the other classes from the Climate Ready Landscape Academy toward sitting for that Watershed Wise exam. So thank you very much for taking this workshop. Let's talk about questions. And I actually have just a couple more things. You're going to receive a certificate of completion after you take your quiz. This gives you the number of CEUs that you have achieved it's 3 for this workshop. And if you want to learn more, stick with the Climate Ready Landscape Academy. We've already done the class on how much water a garden needs. This is a general public class, but it's still a piece of the professional training. So you can take that workshop. It's online, and it will be offered again, I'm sure. And upcoming next month is compost and edible gardening. I recommend you take that. It's essentially a soils class, but we don't call it soils because people don't know they need to know about soils. We've got a gray water class, irrigation timing, a lot of other things that you can take and earn CEUs for.